Hi, I'm Rebecca. During this lesson, we're going to look at a special type of relation called a function. Let's look at our specific objectives. We're going to look at relations and functions, domain and range, determining functions from graphs or equations, function notation, increasing, decreasing, and constant functions. Let's begin with a couple of definitions. A relation is a set of ordered pairs. A function is a relation in which, for each value of the first component of the ordered pairs, there is exactly one value of the second component. Now let's use this definition for the following example. We'd like to decide whether each relation defines a function. Let's consider the first one. We have ordered pairs 2, 4, 0, 2, and 2, 5. Notice that for an x value of 2, there's more than one y value. Here it's paired with the value 4, and here with the value 5. Therefore, this is not going to be a function. How about the relation where we have the first ordered pair, -3, 1, the second, 4, 1, the third, -2, 7. We have three different x values, each are paired with different y values, and so therefore we're going to end up having a function. Now notice that we have the same y value in two places here, but our x values are different, and so therefore this fits our definition for a function. Now let's see how to use the definition of a function while we're looking at a graph. We want to use this graph and decide whether the relation defines a function. Well, we need to go back and think about that definition. Remember that for it to be a function, for each x value there needs to be one and only one y value. For instance, let's take an x value of 4. So I'm going to be looking at our graph and notice that here's a point where our x value is 4, and here's a second point where the x value is 4. For this reason, this is not going to be a function. Notice that both of these points lie on the same vertical line. In fact, what I can notice if I drew a vertical line, let's say over here, where x is 6, I would also have the same situation. Now, what that leads us to is something called the vertical line test, and we're going to look at that now. If each vertical line intersects a graph in at most one point, then the graph is that of a function. And so we can use this idea when we're looking at graphs. If we can draw a vertical line and it will hit the graph in at most one point, we can then determine that this is a function. Whereas if that doesn't occur, then we can say that it's not a function by looking at the graph. Now that we know how to determine whether it's a function by looking at ordered pairs and by looking at graphs, the next thing we want to consider would be equations. And so let's look at the following example. We have x equals y to the 6th power. We would like to determine whether or not this is a function, and we can do so by checking individual values. This might give us a good way to take something that's a little bit more abstract and make it something concrete. For instance, let's let our x value equal 1. In this equation, we would then be saying 1 is equal to y to the 6th power. Now, is there more than one y value that would fit in this equation? Well, you may note that if we take 1 itself and raised to the 6th power, we'll come up with 1. But we can also come up with an answer of 1 if we start with -1. -1 to the 6th power is equal to 1. That gives us then two ordered pairs. We have the ordered pair where we have an x equal to 1 and a y equal to 1, and we have the ordered pair where x is equal to 1 and y is equal to -1. For that reason, we can say that this is not going to be a function. So we can bring it back to the idea of ordered pairs in order to make this determination. Now, for our next problem, we'd like for you to try to determine whether or not we have a function by looking at an equation. Here's the problem. Decide whether the relation defines y as a function of x. Pause the video and try the problem on your own, and then come back and we'll check it together. Now, let's look at the problem together. Remember that the criteria is that for any particular x value, there would end up being one and only one y value. Let's look at what this equation asks us to do to x. The first thing is we take the value of x and we're going to multiply by 2. How many results will you end up getting? Well, for any particular value, when you multiply by 2, there's one and only one result. Once we get that product, we're then asked to subtract the value of 6. If you take a number and you subtract 6, there's one and only one answer. So therefore, starting off with a value of x, we're going to end up with one and only one value of y. And for that reason, we can determine that this is indeed a function. Now, when discussing functions, another big topic has to do with what values our x can actually take on. This is called the domain of the function. If we're interested in what values y can have, this is called the range of the function. Let's look at this for the next example. If we go back to the equation that we were looking at previously, we had y equaled 2x minus 6. What values can we substitute for x? This would be giving us the values of the domain. Well, we can take any number and double it, and we can subtract 6 from any value. So for that reason, we can say that our domain is equal to the set of all real numbers. We're going to write that in interval notation. That will be values from negative infinity up till positive infinity. For the range, we're going to try to determine what values we can come up with for y. Well, for any particular value of y that I substitute into this equation, I can solve and come up with a value for x that corresponds to it. So our range is also going to be equal to negative infinity to positive infinity. I can come up with any value of y I'd like to. As a second example, let's consider the equation we saw previously, x equals y to the 6th power. You'll recall this was not a function, but we can still determine domain and range. What values can I get back for x? Well, notice that I'm taking a number, I'm raising it to an even power, and coming up with x as a result. Notice then that we cannot have negative values here. Our domain, therefore, will only be from the value of 0 and greater. That is written as 0 with a bracket indicating we include the value of 0 on to positive infinity. For our range is going to be the values that our y can have. Well, we can take any number and raise to the 6th power, and therefore our range is going to be from negative infinity to infinity. Now we're going to look at a problem where we're going to use something called function notation, and here's the one that we want to look at. Let's let our function f of x be given by negative 3x plus 4, and we'll have g of x given by negative x squared plus 4x plus 1. The first thing we'd like to do is find g of negative 2. To do this, this means to replace the value of x with the value of negative 2. So we're going to have negative of negative 2 squared plus 4 times negative 2 plus 1. Let's evaluate. We'll have the negative of negative 2 squared is 4. We have a 4 times negative 2, so we can add to that a negative 8. And then we're going to add to that a positive 1. Negative 4 plus negative 8 is equal to negative 12. And when we add 1, we get negative 11 as our result. What if we're asked to find f of 2m minus 3? We'll take the function f and we'll replace our x value with 2m minus 3. That will give us negative 3 multiplied times 2m minus 3 plus 4. Let's use distributive property and simplify. Negative 3 times 2m is going to be negative 6m. Negative 3 times negative 3 is positive 9, and then we add 4, and that gives us a result of negative 6m plus 13. Now, sometimes when we're given an equation, we'd like to put it into functional format. That is, replace the y with an f of x. Let's see how to do that with the next example. An equation that defines y as a function of x is given. Solve for y in terms of x and replace y with the function notation. and then we're going to find f of 3. So to proceed, we're going to take this equation and solve for y. Our first step will be to subtract 4x from both sides of the equation. We'll rewrite this, negative 3y equals negative 4x plus 8. Our next step will be to divide every term by negative 3. So we'll end up with negative 3y divided by negative 3, which is y, equals negative 4x divided by negative 3, which can be written as 4/3 times x, plus 8 divided by negative 3, which is going to be written as negative 8/3. Now we're going to replace y with the function notation. That can be accomplished by just rewriting this as f of x equals 4/3 x minus 8/3. To complete the problem, we're asked to now find f of 3. And so we're going to take this equation and now replace our x value in the equation with 3. So we're going to have f of 3 equals 4/3 times 3 minus 8/3. Because I'm going to end up having to subtract these two, I'm going to go ahead and evaluate this by just writing 4/3 times 3 as 12/3 minus 8/3. And that's going to give us a result then of 4/3. And so we come up with our answer, f of 3 is equal to 4/3. That means that when our x value is 3 in this function, our y value is equal to 4/3. We can also use the graph of a function in order to help us find function values. And so we'll see how to do that in the following example. Here we're given the graph of a function y equals f of x, and we're going to be asked to find 4 function values. To use our graph, we're going to start by remembering that the expression inside the parentheses is actually an x value. What we're going to be trying to find is a y value, since y is equal to f of x. So to begin with, let's try to find f of negative 2. That means look at the graph where x is equal to negative 2. And if we move over to the left, we're looking then at this point. What is the y-coordinate of that point? Well, the point lies on the x-axis, meaning that we're not moving up or down off of the x-axis, so our y-coordinate is 0. Let's do the same thing for f of 0. That is, start with an x value of 0, which means we're not moving to the right or the left off of the y-axis. We notice that on the graph, we have this point whose y-coordinate is 4. So we're going to say f of 0 equals 4. F of 1 can be found by finding where x is equal to 1 on the graph. That corresponds to this point. The y-coordinate of that point is 2. And f of 4, we look for an x value of 4, which is going to be this point on the graph. The y-coordinate of that point is also 4. And so f of 4 is equal to 4. Finally, let's look at a graph where what we're going to be trying to do is to determine intervals on which a function is increasing, decreasing, and constant. And the graph that we're going to use looks like this. Here, we notice that we have the portion of the graph to the left, it continues to the left in that manner. And then we have a section of the graph which runs horizontal, and then we have the section of the graph that goes off in this direction. What's key to working this problem is remembering that we always read a graph from left to right. Therefore, when you're trying to determine whether the sections are increasing or decreasing, don't be confused about the fact that this looks like the arrow is going upward, and therefore you might think increasing. If you're moving along the graph from left to right, what is actually going to be occurring in this interval? This entire interval is going to be decreasing. Now, because we move from left to right, we always write our answers in terms of our x-coordinate. So we're going to start off by writing the fact that this graph is decreasing from, and we're going to start over here, furthest to the left, negative infinity. And then it continues decreasing until we come up with this x-coordinate at negative 1. Then we notice that we have a section of the graph moving left to right which remains constant. we write down that interval from this x-coordinate to that x-coordinate, and that's going to be from -1 to +4. Then the section that's to the right, past an x value of 4, is moving upward, and therefore we say that that is increasing, and it is increasing on the interval from this point all the way to the right, which would be from +4 to +infinity. Now this section has looked at a number of problems involving graphs and the idea of functions. Try some problems on your own now from your textbook in order to become more familiar with these concepts.